Hi everyone, my name is Roxy Rahimi.
Hi, my name is Roxana Rosenthal.
Hi, my name is Alba Fahim.
Hi, my name is Ella Jalili.
And today we'll be testing the non-polarity between the balloon and the orange peel. Now, when I take an orange peel against this balloon, let's see what happens.
Oh my god.
So, as you guys could see, the balloon popped. Do you want to try it? Oh, will work better.
Oh my.
It worked!
Oh.
The orange.
Oh my god.
Oh.
Daddy, it's unpoppable! So my guess is the reason why this happened, that the orange wedge popped the balloon is, I guess like all the, maybe like the acid in the orange, I guess.
Okay.
Maybe gave it like, yeah.
I think that happened because, well, I think maybe like the edge of the wedge might have helped a bit, but also like Roxana, I think there might have been some chemical or acid in it that like made the balloon pop.
I think the orange peel made the balloon pop because of the acid, and it like maybe like melted away some of the rubber on the balloon, and it made it pop.
Okay. What do you think oranges are made of?
Citrus and acid.
Okay.
Seeds.
What are oranges made of?
Oh yeah.
So you guys said citrus. What else?
Acid.
Acid, which is a citrus.
Citric acid?
Well, yeah, citric acid. What else?
Matter?
Matter. Seed.
Seeds, water, yeah. It is a liquid after all. Well, when you juice it. But there's also something in it called limonene. Now, limonene, we'll learn about it and why that's significant exactly. So when we look at limonene, the chemical structure of limonene looks like this. So it's, as you can see, it's a hydrocarbon, sorry. It's a hydrocarbon because it only has carbon, which that stands for carbon, and hydrogen, which that's what H stands for. So we have a hydrocarbon. Hydrocarbon, okay. And that's the structure. So it's only made out of hydrogen and carbons. So now, why is this exactly important? Well, hydrocarbons...
The computer turned on.
Can you turn it on? Hydrocarbons are non-polar. We'll learn about polarity and what the significance of that is. Where did my red marker go?
Oh, it's right there.
So, what are polar molecules? The basics are that it has a positive and negative charge on each end. On each side. And it's asymmetrical, so it's not symmetrical. Now, non-polar, which is what a hydrocarbon is, it's pretty much the exact opposite. So, it has no positive and negative side. It's pretty even. And it's symmetrical. So, the exact opposite of polar because it's non-polar. And I'll draw out a molecule representing each polar and non-polar so you guys get an idea. Alright, so I'm going to draw an example of a polar molecule. So let's say we have 2 here and 1 here. So the reds are the same, clearly because they're the same color, and they're connected like that. So as you can see, this is asymmetrical. We won't worry about the charges just yet. I'll draw another example displaying that. But let's look at a symmetrical example which shows nonpolar. Let's see, like this. Okay, so this is more symmetrical. And I'll show you guys an example of positive and negative end now. Okay, so let's first look at nonpolar. So let's say we have a green dot and a green dot and then a black dot in the middle. And they're all connected. Now let's pretend that these green dots are negative and these are positive, that in between these are negative again. So as you can see, this is pretty linear. It goes in a straight line or in a constant, constant like way. And let's draw a polar molecule and I'll explain the difference in a bit. Let's say we have the polar here and then they're connected, and let's say the top ones are positively charged and the bottom ones are negatively charged. Now when we draw a line in the middle of these two, let's draw a line. Look, it has a positive side and a negative side. Do you see that? But when we draw a line through this, it doesn't have a positive and negative side. Both sides are positive and negative. So that's the difference between nonpolar and polar. Now, we talked about limonene, the citrus oil, what makes an orange an orange. Inside of an orange being nonpolar. That's the component that's going to be important today. Now, let's talk about limonene again. So, you guys could look at the structure of limonene again. It's right over here. And so, it's a nonpolar hydrocarbon. Just to remind you guys. Now, what are balloons made out of?
Rubber.
Balloons are made out of rubber, yeah. Anything else you guys can think of? Air, sure. They're filled up with air. So we'll be focusing on rubber right now. And rubber is also actually nonpolar. So rubber is nonpolar as well. So limonene and rubber are nonpolar. So 2 nonpolar substances. And this is the structure of rubber. You could read it. You guys could examine it. It's the chemical structure. And it's a nonpolar structure. Now, if balloons are nonpolar structures are known to dissolve each other. So 2 nonpolar structures are able to dissolve each other. So basically, the limonene is dissolving the rubber in the balloon.
Oh.